So hello everyone, welcome back to our lecture session. So you are looking at a mixing problem, right, when we mixed solution A and solution B with different pH and different alkalinities, and we end up calculating the pH of the mixture. And I believe we looked at two cases, one how to work it out by hand, and one obviously how to work it out by Wien-Mintek, which usually ends up being faster and more efficient too. Right, again, but you need to have a grasp of the fundamentals, otherwise you are going to go MS. That is the reason we try to work it out by hand. Yes. So here we have two other parts of the same question, but some of them, or at least the third one, is a bit more complex. So let us try to see how we can go forward, right. So let us just look at this next part of the question. We have what would be the pH of the mixture if it were allowed to equilibrate with carbon dioxide in the atmosphere. So earlier, let us say this was a closed system, right. And now what are we considering it here, that it is a open system, right. So let us go back to Wien-Mintek here, and we already plugged in the relevant values, and I think we ran the Wien-Mintek. Where is the output? So we had a pH of 7.8, right, but this, as we just looked at it, is for a case of the closed system. And now we want to look at how do we go about it if the partial pressure of the carbon dioxide. So now your solution, let us say, is now in equilibrium with this partial pressure of carbon dioxide, and that is given as 3.8 into 10 power minus 4 atmospheres, and this is your solution that you looked at initially in case A, right. So now what is the new values or such? So we need to look at some of the relevant aspects. So again, what are these aspects that we need to look at? So if we remember what we discussed with respect to alkalinity, and if you can recollect what we discussed, right. So if you bubble carbon dioxide to the solution, obviously H2CO3 is going to be increasing or not increasing, let us say, depending on the concentration. H2CO3 concentration is going to be affected, and let us say now it can increase in this particular scenario, let us say, thus the pH will come down, that is fine. But we did look at the relevant equation for alkalinity, and we saw that bubbling carbon dioxide through the particular solution or equilibrium with carbon dioxide will not affect alkalinity in any manner, right. So alkalinity is going to be constant. So that is the key aspect that you need to consider here. So again, like earlier or similar to the previous case, we are just going to understand how to get this done by hand, right. So what are the fundamental aspects here? So here we have alkalinity is equal to alpha 1 plus 2 times alpha 2 into CO3 total plus Kw by H plus minus H plus, right. This is something that we have used in the previous session too, so I do not need to elaborate. So again, first we are going to look at how to calculate this by hand. So the key is we have, let us say, alkalinity, yes, but we do not have CO3 total, right, and why is that? Now your partial pressure of CO2, right, that is going to equilibrate with your solution now, right. So there is going to be an exchange of CO3 total or CO2 here in this case between, and here H2CO3, right. So the CO3 total will change here, yes, more or less CO2, it is nothing but a component, you can express it in terms of CO3 2 minus, or it is going to thus affect CO3 total. So the CO3 total in the liquid phase plus CO3 total in the gaseous phase is equal to the CO3 total, I guess, right. I should have expressed that in a better manner, but here we are going to consider this particular case, yes, while the total CO3 of the entire system is going to stay the same, because there might be an exchange of CO2 between the gaseous and the liquid phase, the CO3 total in the liquid will change them, yes. But one key aspect that we discussed was that alkalinity, which we defined as, how did we define that? All the bases, what were they? OH minus and HCO3 minus and 2 times CO3 2 minus, right, minus H plus. This is not going to be affected when you increase the carbon dioxide concentration. So why is that? So CO2 will equilibrate in solution with H2CO3, right. So H2CO3 can either dissociate to H plus and HCO3 minus, or if I look at complete dissociation, H2CO3 can dissociate to 2H plus and CO3 2 minus. So if I plug in, let us say, this particular case here, in this equation, what do I see? One HCO3 minus increases, but then H plus also increases, so both of them cancel each other out, so there is no effect on alkalinity. So same case here again, if I look at the case where H2CO3 completely dissociates, so increase of 2H plus and increase of 1 of CO3 2 minus but because of the equivalence the effect is going to be twice. So 2 times that minus 2 times of H, so again that is going to cancel each other out, and again there is going to be no effect on alkalinity. So again we are just trying to refresh what we discussed in the previous classes, that if you bubble carbon dioxide through the solution, so you might or you will probably see a change in the pH, right, but you will not see any change in the alkalinity of your particular solution, right. This is the key that we are going to look at. So again looking at some of the few aspects what we discussed earlier, so we need to come up with a way to understand the CO3 total of the system, right. In this case obviously we were trying to look at Henry's constant, right, Henry's constant, which is usually expressed as H. What is that equal to? Concentration in the or activity in the gaseous phase by activity in the aqueous phase, right. So gaseous phase activity we look at partial pressure, and in this particular case in activity of H2CO3, right, which I am going to approximate obviously by the concentrations PCO2 by H2CO3 concentration, right. So this is the particular case for Henry's constant, which the units are atmospheres per molar units, right. But let us say I am going to consider another particular case of what is a moles per molar per atmosphere units. So then it is going to be equal to H2CO3 concentration by partial pressure of CO2, right. Again Henry's constant has different units when the units are atmospheres per molar units. So this is the particular definition obviously. When obviously you know I am going to look at the inverse units, same case I am going to just look at the inverse of the variables here, right. Anyway you know people use them depending on the situation. So here I am going to look at this particular case of Henry's constant, right. So how can I further simplify this? We talked about this earlier, so I am going to write this down here. KH is equal to what now? Alpha naught times CO3 total by partial pressure of CO2, right. That implies that CO3 total, which is what I am going to calculate, is going to be equal to what now? KH times PCO2 by alpha naught. Again keep in mind that in this particular case KH, the units of the Henry's constant are molar units per atmosphere, not atmospheres per mole, right. So that is the one case that we are going to look at. Again this is something we derived earlier. So now I can plug this in here, right. Let me just write this down in the next particular slide. So I have alkalinity plus or is equal to, pardon me, alpha 1 plus 2 alpha 2 into CO3 total plus Kw by concentration of H plus minus concentration of H plus. So now we had a new relationship. What was that? We had CO3 total was or is equal to KH into partial pressure of CO2 by alpha naught. Is that right? KH, yes, that is right. So I can plug this in this equation. So now I will have alpha 1 plus 2 alpha 2 into Henry's constant, obviously it is a constant, partial pressure of CO2 by alpha naught plus Kw by concentration of H plus minus concentration of H plus, right. So what do I have here? I know that by bubbling carbon dioxide through solution the alkalinity does not change. So I still have the alkalinity, right. In this particular case alkalinity is a known what do we say, known value, yes. And what else do I have? I have the partial pressure of CO2, yes, and from this I can solve for what now? I can solve for H plus concentration, right. So the only unknown in this particular equation, what is that now? It is H plus, right. Again as you know alpha 1, alpha 2 and alpha naught are just functions of H plus. So from this particular case I can solve for H plus, and obviously I can now analyze the system, right. So this is by hand. Obviously again it is going to be tedious now to be able to solve these particular what do we say this particular equation. Obviously you can use Excel and solver function within that, maybe depending on time we can look at that later. But now we are going to skip through and look at how to calculate this particular or go through by Vmintek, analyze this system by Vmintek, right. So let us switch back to Vmintek, and where do we have that here? And view edit list, this is something we already have plugged in from the previous lecture session. These were the values of H total and CO3 total we calculated from the component balance, right. And now though I need to have a new case or new variable. What is that? Obviously, okay, and the case is that now I have new partial pressure of CO2 that is in equilibrium, and what is that? It is 3.8 into 10 power minus 4 atmospheres, right. So I need to go back to Vmintek here. So I am going to gases and specify. So here I can specify different gases as choose a gas among the database, but because it is carbon dioxide, you know, that is something usually built in, okay. So here atmospheric partial pressure is 3.8 into 10 power minus 4 atmospheres, which is given, and you can specify a multiple of that if you want to. But in our question, I guess for sake of ease, we already have the PCO2 given as 3.8 into 10 power minus 4. So I don't need to change this particular multiple. For example, it was 7.6 into 10 power minus 4, then I can change this to 2, right? But here it's just 3.8 into 10 power minus 4, which is similar to our question. So I'm just going to leave that as 1. I'm going to add that, right? So if I look at list of fixed species now, there's going to be an additional species which is carbon dioxide, right? And back to main menu, and now I'm going to run vmintech, I guess, yes. And there was some minor issue here. Let me go back to looking at this particular case. Where is this view edit list? And okay, so that's fine. And so obviously now the pH is now higher, and what is it now? It's going to be 8.98, right? So what does that tell you though? Where is this particular case? So now the pH we end up with was 8.98, and earlier the pH we calculated was 7.88, right? So earlier case 1, when we had just the solution, the pH was 7.88, and now when we have it in equilibrium with partial pressure of CO2, the pH came out to be 8.98. And why is that? Let us say maybe because the partial pressure that would be in equilibrium with 7.88, that is going to be higher, let us say. So what happened was carbon dioxide or H2CO3 entered into the system or left the system, right? And that is why you had an increase in pH, and that is what you see here, pH is 8.98. So in this particular case, what happened now? Carbon dioxide or H2CO3 left the system, and that is why you see an increase in the pH. So just for sake of analysis or try to understand the system, let us try to increase this particular value and see what you would come up with. So I am going to go back to input menu, going to go back to gases. So here let us say instead of 1, right, I am going to have, let us say, let me go with 5 for now, random value, add, and back to main menu, and again run mintech, right? And so again now you see that the pH has fallen, but not to a great extent. It has now fallen to 8.3. Let us go back and change it again or increase the concentration, and let us say I am just for the sake of this is a theoretical aspect, right, 100 let us say, right. I am going to add that and back to main menu and run mintech, and now you see that the pH is starting to fall further, right. So let us go back to our particular case. So what do we see here? When there was no partial pressure of CO2 or CO2 with equilibrium, we end up with I think something around pH of 7.88, closed system. When it was an open system, right, there was no partial pressure of CO2 here or no CO2 in equilibrium with this particular solution, open system. So this was the closed system. We end up with pH of 7.88. And when we took an open system, when let us say your particular solution could be in equilibrium with a solution at partial pressure of CO2, not solution, pardon me, the gas of partial pressure of CO2 at 3.8 into 10 power minus 4 atmospheres, right. And what happened now? We saw that the pH increased to the particular value of 8.98, pardon me, right. And why is that? Because you can obviously understand that. So the pH increased. What does that mean now? If the pH decreased, you would have understood that let us say CO2 entered the system, right, and formed H2CO3. But here in this case compared to case A, case B, you see that the pH increased. It is now 8.98, right. So what does that mean? So H2CO3 left the system, right. So thus the pH decreased, not decreased, pardon me, the H plus concentration decreased. So thus the pH increased. That is what we see here. So just to illustrate that, I end up, what do we say, increasing the concentration of partial pressure of CO2 to 100 times this value of 3.8 into 10 power minus 4, right, or 3.8 into 10 power minus 2. So in that case, when I increase that partial pressure of CO2, the case 3, let us say PCO2, I increased to something around, what is it now, 3.8 into 10 power minus 2 atmospheres, right. And then I think we came up with a particular value. What was that? We came up with pH of 7.0, right. We came up with a value of pH of 7.02. So I increased it by 100 times compared to this case 1 and case 2, right. So compared to this particular case, what is happening here? So case 1 again we looked at 3.8 in 10 power minus 4, we see that CO2 left the system, that is why the pH increased. But case 2, when I increased the partial pressure of CO2 to a very high value, which was 100 times given in this case 1, I see that the pH fell. So what does that mean? It means that CO2 entered the system, right, H2CO3 was formed, and that is why the pH fell. In this case, what do I understand? That the CO2 left the system, right. So that is what you see here, and that is the difference between this case of 8.98 pH and pH of 7.02, right. So again let us go back to the Vmintek here, right, and we will try to solve for the last question here. And so this is a slightly complex case obviously, and what do we have here? What would be the pH of the solution if 10 power minus 3 molar HCl were added after it equilibrated with the atmosphere? So the key is now we are adding 10 power minus 3 molar units of HCl, right. So let us see how to analyze the system. So first we need to obviously have the relevant values from the previous run or iteration. So let us go back to Vmintek. So I am going to go back to gases again. So the case was that it is 3.8 into 10 power minus 4, so I need to get that back there, okay. So I am going to add that here, back to main menu and run Mintek, right. So obviously again we are going to have that pH 8.98, right, because I decrease the concentration of partial pressure of CO2 or decrease the concentration of CO2 gas. So now I need to again calculate CO3 total, right, and H total. So I am going to do that here, yes. Let us go to print to Excel. Let us try to calculate CO3 total first. So that is going to be equal to H2CO3 plus HCO3 minus plus CO3 2 minus and enter. So we have something like 6.1 into 10 power minus 3. So now we are going to try to calculate H total. So H total is equal to H plus minus OH minus plus 2 times H2CO3 plus HCO3 minus and enter. So now I have two values here. What are they? 6.1 into 10 power minus 3, and let me write this down, right, so that we do not skip through that again. My Excel slide here is somewhere here, okay. It is 6.1 into 6.148 into 10 power minus 3. And what is my H total? H total is equal to 5.836 into 10 power minus 3. Right. So that is what we have here. So again let us go back to the question and understand that, understand where we are at, right. So here again the key is that we need to analyze the system from part B. Why is that? Because this says, the question number C says, or part C says, we are adding HCl but after the solution equilibrated with the atmosphere, right. So that is why I am going to go with that, right. And how much HCl am I adding? 10 power minus 3 molar HCl. So let us go back to this particular case, Vmintek, back to input menu. So now there is no more gas, it is already after equilibration. So let us say I am going to list of fixed species, delete this species, right. And why is that? Because now we do not have that particular equilibrium anymore, but now I am going to change my particular scenario here with respect to H total. And why is that? Because I added HCl, right, at, so that is HCl naught at 10 power minus 3 molar concentration, right. That is what we have here. So obviously what is going to change here? There are ones we are going to look at it by hand, yes. So what is going to change is CO3 total going to change, think of that now. So what are the aspects that are going to change now? CO3 total, it is just H2CO3, HCO3 minus and CO3 2 minus, but you are just adding HCl. So there is no effect on CO3 total, so that is going to be a constant, yes. That is, so that is one particular aspect. Obviously the pH will fall because you are adding H plus or HCl, a strong acid, so that is something you need to calculate. So what else can you calculate though? So you know the alkalinity from the previous session, right, or you know the session before that, you know the alkalinity, and you can calculate by subtracting this particular acid concentration from alkalinity, you can calculate the new alkalinity. What am I trying to say here? Let us try to plug this in. So, alkalinity, after addition of HCl, I will have this is going to be equal to alkalinity initially from part B, right, minus concentration of acid or strong acid added, right. And why is that again? Just think of this now. Alkalinity is, the equation was H2CO3, pardon me, HCO3 minus plus CO3 2 minus into 2 plus OH minus H plus. So, when I am adding HCl, what does that mean? That means I am increasing the concentration of H plus, or adding acid here, right. So, that means alkalinity is going to decrease. So, that is why I say that in part C, I guess, right, we are in C. So, alkalinity after addition of HCl is going to be alkalinity initially that we calculated from, or we can calculate from part B minus HCl naught, right. So, what is that equal to now? Let us try to see that here. That is equal to 6.4 into 10 power minus 3, right, minus, and what is this particular case? It is 1 into 10 power minus 3. So, that is equal to 5.4 into 10 power minus 3, right. That is the alkalinity for this particular case. That is going to decrease by the amount of acid you plugged in. And what else do we have? We also have CO3 total, that is given, right, and what is that equal to? CO3 total equal to 6.148 into 10 power minus 3, or let us say 6.2 into 10 power minus 3, right. So, by hand how can I solve this? I still know that the alkalinity equation. So, I have this particular here. So, alkalinity is equal to alkalinity with HCl after addition of HCl, which is this value, is equal to alpha 1 plus 2 alpha 2 into CO3 total plus Kw by H plus minus concentration of H plus, right. So, what do I have here? I have alkalinity after addition of HCl, which we just calculated here, right. I also have CO3 total. So, this is from part B more or less, right. So, I calculated this, or I have this, let us say, and I just need to now be able to solve for H plus, right. So, that is the only unknown. So, I can solve for H plus here again, and I will be done with my particular scenario, right. So, now let us look at how to solve this by V-Min-Tech now, right. So, what can I do here? Let us say, or alternatively I can also look at total H by hand. So, that is something we are going to just discuss. So, how can I do that? So, total H, how much did we calculate that to be? Total H was 5.836 into 10 power minus 3, 5.836 into 10 power minus 3 from part B, right. So, in part C, right, what am I doing? I am adding HCl, right, at 10 power minus 3 concentration. So, what does that mean? The total H, or H total after addition of this HCl is going to be H total initially plus addition of the concentration of this HCl, right, and what is that equal to? 5.836 into 10 power minus 3, that is H total initially from part B, plus how much acid am I putting in here? That is going to be equal to 10 power minus 3, right. So, that is going to be equal to 6.836 into 10 power minus 3. So, again earlier we looked at it with respect to CO3 total and alkalinity, right, after addition of HCl. Another way to calculate by hand is to look at the effect on total H, and how is that? So, how are you increasing or how are you affecting H total here? So, H total, right, you are only adding acid, which is going to be affected by increase in H plus. So, that is why H total after addition of HCl is going to be equal to H total initially plus the concentration of strong acid that you are plugging in. So, strong acid meaning I am assuming that everything or all the acid is going to dissociate. So, all the H plus is going to be donated, what do we say, donated here, right, or is going to stay in the solution. So, that is why I have HCl here, and with that I now have H total given here. So, from this what can I calculate? I know that H total is going to be equal to H plus minus OH minus plus 2 times H2CO3, right, plus HCO3 minus, right. This is our usual case. So, H total after HCl though, right. So, this H total after HCl addition is going to be equal to H plus minus Kw by H plus, right, plus 2 times alpha naught plus alpha 1 into CO3 total, right. So, what do I have in this particular equation? This is a known value, alpha naught and alpha 1 are functions of H plus, and CO3 total is a known value which we calculated here in the previous slide. So, here this is just a function of H plus, and now I can calculate after by hand or manipulation or using Excel, let us say if you want to, I can calculate H plus. So, we looked at two cases when we looked at the effect on alkalinity, which is going to decrease because you added HCl, or on H total, which is going to increase because you are adding a strong acid, right. So, here there are two cases. So, the next case is how to solve this by V min tech. So, V min tech. So, how do I solve this now? So, again I am going to plug in H total after addition of HCl, and also what else please, CO3 total after addition of HCl, which is still going to be CO3 total initially, right. And why is that? Because HCl is not going to affect CO3 total, yes. And here H total HCl, what was that equal to? Let us look at that. H total after HCl addition was equal to 6.836 into 10 power minus 3, 6.836 into 10 power minus 3, right. And what was the CO3 total value? Did we calculate that somewhere? CO3 total was 6.148 into 10 power minus 3, 6.148 into 10 power minus 3, right. So, by V min tech, let us see how we can cut down on the time and make it more efficient. So, again in V min tech we just need to plug in the values of the total components, and which is what we are going to do. So, I am going to switch to V min tech here. So, obviously first case is I need to check that there are no gases, right, list of fixed species, so nothing here. So, and then I need to edit my list, and what is the concentration of H plus here? I need to look for that here please, 1 second. Okay, H total is 6.836 into 10 power minus 3, right. So, let me plug this in 6.836, right. Okay, and next I need to edit the CO3 total, and I need to first have that particular component here, CO3 total. So, now I need to check it's 6.148 into 10 power minus 3. So, 6.148, so 148 into 10 power minus 3, I am going to add that to the list. So, view edit list 6.836 into 10 power minus 3 and 6.148 into 10 power minus 3, and back to the main menu, right. And now I am going to run min tech. Now obviously I see that the pH is now less, it is 7.2, right. So, let us understand the system here. So, I now end up with a pH of 7.2, right. So, let us go back to that particular case where we looked at comparison of different pHs here, this case. So, initially for closed system it was 7.8 from part A, right. For part B, after we let it equilibrate with the atmosphere 3.8 in 10 power minus 4, we saw that the pH increased to 8.98, and why is that? Because CO2 left the system. And in part C, considering this solution, which is now let us say assuming it is a closed system again, not open to the atmosphere anymore. So, the initial pH was 8.98, we can calculate the CO3 total, we can calculate H total, right. And from this particular case we plugged it in V min tech, and we end up with a value of, what is that please, 7.2, right. So, obviously why is that? Because I am adding a strong acid HCl naught of concentration of 10 power minus 3 molar, right. So, again let us just try to understand system, closed system, different cases given, right, and we end up with a pH of 7.8, open system, CO2 escaped into the atmosphere, and thus our pH increased, yes. So, CO2 left the system, yes. So, in effect H2CO3 left the system, right. So, that is why the pH increased, and that is why it went to 8.98, and then after that we add again HCl, right, and then obviously you are going to see a decrease in the pH, and that is what you see here, right. So, we are now at this stage you should now be comfortable to understand the basics or the fundamentals behind the acid base systems, and also be able to use V min tech to be able to solve your particular scenario, right. So, with that we will end today's session, and in the next session I believe we are going to look at the last aspect with respect to acids and bases. That is going to be the case when your theoretical definition of alkalinity is not consistent with the practical measurement that you come across, okay. And with that I will end today's session, and thank you.